the problem is fx equal to x minus x e to the power minus 1 by x when x greater than 0, then we have to prove this function is an increasing function on the open interval 0 infinity, and also we have to find out the limit of fx at x tends to infinity. Now let's start. Here we have to prove this function as an increasing function. We have already known the condition of a function to be increasing or decreasing. If a function is an increasing function, then its derivative, that is function's derivative with respect to independent variables, is greater than 0. And if it is decreasing function, then its derivative is less than 0. So, to prove this function as an increasing function, we have to check the sign of the differentiation of fx with respect to independent variables x. If the sign is positive, then this function is obviously an increasing function. So, our job is to check the sign of the differentiation of the function fx. Here fx equal to x minus x e to the power minus 1 by x, also x greater than 0. So we can differentiate this function with respect to x, that is dx of fx equal to 1 minus x into 1 over x square e to the power minus 1 by x. This is the differentiation of fx with respect to x. So we can write 1 minus over x, 1 minus 1 over e to the power 1 by x minus 1 over x into e to the power 1 over x equal to 1 minus x e to the power 1 over x. Numerator is x plus 1. Now, this is the differentiation of fx with respect to x, that is dx of fx. Now, we can take the series expansion of exponential function 1 by x, e to the power 1 by x. We can take the series expansion of e to the power 1 by x. So, the series expansion of it can be written x plus 1 x into 1 plus 1 by x factorial 1 by x square factorial 2 up to infinity. So, dx of fx equal to 1 minus x plus 1 over x plus 1 over factorial 2x 1 over factorial 3x square dot. This is, and also we can say x plus 1 over x plus 1 plus 2 factorial x 1 plus 1 over 3 factorial x square. This expression expression, but this term is also less than 1 for x greater than 0. This term, the value of this term is less than 1, always less than 1 if x greater than 0. So, derivative, so we can also write minus, if we multiply both sides of this inequality, we get minus x plus 1 over x plus 1 over 2 factorial x 1 over 3 factorial x square dot greater than minus 1. If we multiply both sides of this inequality by minus 1, minus sign, then we can get this inequality. Inequality is changed with was less than 1, and now it is greater than minus 1. So, if we add up both sides of this inequality by 1, if we add both sides by 1 minus x plus 1 over 2 factorial x 1 over 3 factorial x square greater than 1 minus 1 equal to 0. That is greater than 0. So, we can write from this expression, from this inequality, we can write ddx of fx is also greater than 0. So, ddx of fx greater than 0. This is the condition of an increasing function. This is the condition of an increasing function. If the function's derivative with respect to independent variable is greater than 0, then this function is an increasing function. So, here this is an increasing function because derivative of fx greater than 0. Derivative of fx greater than 0 with respect to x, derivative with respect to x, fx greater than 0. So, we can say this function is an increasing function. So, this implies fx is an increasing function. Increasing function. Now, we have proved the function fx is an increasing function, and next week we shall prove the limit of this function at x tends to infinity is 1. Our next proof is limit x tends to infinity fx equal to 1. First proof is done. So, second proof is to be done. Now, our second proof is limit x tends to infinity fx equal to 1. So, we write limit x tends to infinity fx equal to limit x tends to infinity x into x minus x e to the power minus 1 over x. Limit x tends to infinity x into 1 minus, after factorizing these terms we get this, also we can write limit x tends to infinity 1 minus e to the power minus 1 over x over 1 over x. Now, if we put x equal to infinity on both numerator and denominator, if we put x equal to infinity on both numerator and denominator, we get the form 0 by 0, 0 by 0 form. Zero by zero form. this is 0 by 0 form. If we put x equal to infinity on both numerator and denominator, then we get this form. We can get this form 0 by 0. If in any limit we get 0 by 0 form or infinity by infinity form. In any limit we get if we get 0 by 0 form or infinity by infinity form, then we can take the L'Hospital rule to evaluate this limit. To evaluate the limit, we can use the L'Hospital rule because the limit is in the form of 0 by 0. Numerator and denominator both are 0. If we put x equal to infinity, then this is 0 by 0 form, and as it is 0 by 0 form, we can use the L'Hospital rule to evaluate this limit. So we use the L'Hospital rule to evaluate this limit. To use L'Hospital rule, we have to differentiate both numerator and denominator with respect to x. This is the L'Hospital rule. L'Hospital rule is to differentiate both numerator and denominator with respect to x. So we shall differentiate numerator and denominator with respect to x. After differentiation, we get minus 1 over x square e to the power minus x 1 by x minus 1 over x square. So this can be written as x tends to infinity. 1 over x square, 1 over x square is cancelled out. That is, if you divide these two terms, 1 by x square by 1 by x square. After division, we get minus 1 by x minus this is, as we can divide these two terms because x not equal to infinity. X not equal to infinity, as x not equal to infinity, we can divide these two terms 1 by x square and 1 by x square. If divide 1 by x square by 1 by x square, we get 1. So we can get this limit, and also this limit is 1 because e to the power 1 minus 1 by infinity equal to 0. 1 by infinity equal to 0, and so e to the power 0 equal to 1. So this value of this limit is 1 at x tends to infinity. So value of the limit is 1 at x tends to infinity. So we have derived limit x tends to infinity fx equal to 1, and previously we have derived fx is an increasing function. Fx is an increasing function. So we have proved that the fx is an increasing function, and also its limit is 1. Thanks for watching this video.